Currently, there are believed to be two classes of GRBs, but we are concerned with only the long-duration GRBs, or LGRBs, which are due to the death of supermassive stars. When we first view these events, what we see is a prompt gamma ray emission, but after a few hours or days it is followed up by emission from lower energy frequencies such as radio, which is what we're primarily concerned with. Recently, there's been a discovery of two possible classes existing in the radio emission, those being radio loud LGRBs and radio quiet LGRBs. We believe there are two possible origins for these classes. It could either be due to selection effects, which is the stance I'll be taking, or it could possibly be due to physical origins as is shown in the results of Lord 2019, which I'll refer to as L19 from here on out. So, if we look at figure 2, we see in the intrinsic duration, or T90Z distribution, that there appears a separation, where the radio quiet bursts tend to have a lower duration than those of the radio loud GRBs. Similarly, in the isotropic gamma ray emission, or EISO, the radio quiet GRBs seem to be concentrated toward much lower energies as compared to those of the radio loud GRBs, which span a larger range of values. This is the first hint that there may indeed be two separate classes. Lastly, when looking at the redshift, the two distributions seem to be almost exactly the same. Most importantly, however, is the apparent anti-correlation between the T90Z and redshift in figure 3 within the radio loud sample, but the lack of such correlation in the radio quiet sample. With that being said, I would like to now move on to why my research group and I believe that this relationship may actually be due to factors not related to radio emission of GRBs. We believe that the two classes of radio loud and radio quiet GRBs are likely due to selection effects as well as a non-zero correlation between gamma ray and radio emission. In figure 4, the red oval represents the non-zero correlation. From here we also have the gamma ray detector threshold, and so anything below this line will not be observed. We also have a radio telescope detector threshold where anything to the left will not have a radio emission detected and anything to the right will, and it will be called radio loud. Lastly, we have a classification limit where any GRB with an EISO value above this will have a radio emission detectable by a radio telescope and classified as such. So how do we prove our hypothesis? Well, we began doing what is depicted in figure 5. We first convolve our observed properties with our redshift model, which is grade distribution, in order to find the intrinsic distribution, which is red. We then take our newly found intrinsic distribution and convolve it with our observed properties to better constrain the redshift distribution. Finally, once we have constrained our distributions, we can then generate a set of attributes for such as EISO, T90Z, and redshift given a randomly selected set of parameters for the LGRB world model. From here, we can then construct our LGRB world, which can be seen in figures 6A and 6B. In plot A, we have our T90Z on the y-axis, and along the x-axis, we have our EISO associated with each GRB is also the probability of being seen by our detector, which in this case is the Swift satellite. The probability of detection for each burst is represented by the colors on the right side, with magenta being 100% chance of detection and cyan being 0% chance of detection. Colors in between are 0 and 100%. There's also a cutoff criterion around 10 to the 52 ergs that was made in Lloyd 2019, which we abbreviated as L19. Additionally, we also have a classification limit from plot 4. The yellow points represent the radio loud GRBs and black points represent the radio quiet GRBs from the L19 data. Plot 6B is similar to 6A, except that the y-axis we have EISO and on the x-axis we have the redshift. What we can see here is quite apparent. The radio quiet samples have been sandwiched between these two artificial limits, which in turn limits their possible values, compared to the radio loud sample, which is limited only by the artificial cutoff made in L19. Now we come to the most important plot here in figure 6C. On the y-axis we have the correlation between EISO and redshift. On the x-axis we have EISO and T90 correlation. And lastly, the gradient of colors represents the correlation between the redshift and T90Z. So if we look first at radio quiet sample, which is blacked out, we find a high anti-correlation between EISO and T90. And this point also corresponds to a very insignificant anti-correlation between our redshift and T90Z, just as seen in Lloyd 2019's paper. Now, in contrast to this, the red point on our plot, which represents the radio bright GRBs, shows significant correlation of about 0.3 between EISO and T90Z. More importantly, though, is that the point clearly falls in the area where there's a significant anti-correlation between the intrinsic duration and redshift, like in L19. So we've shown that we're able to reproduce the same correlation between redshift and T90Z, relying solely on the isotropic gamma ray emission, and did not care whether our bursts were actually radio loud or quiet. So in conclusion, it's always important to consider any biases you may unintentionally introduce into your problem, as well as incompleteness in your sample.